I think we all.
Okay, I guess we should get started for today. Are there any questions about anything from the last lecture, or are there any issues yet on the homework? Okay, just to remind everyone, on Thursday we won't be meeting for class at the usual time, so I'll be presenting at the Science 2014 thing, so you're not required to go to that. I'm suggesting that session is something I think many of you will find interesting, so I recommend attending that session. It's on sequencing technologies, basically, in place of class this Thursday. And for the homeworks, if you don't turn them in online, please bring them to my lab. You can leave them under the door there, but please plan to be in class, or excuse me, please plan to bring your homework by, I think I said 5 p.m. on Thursday. Is there any questions on any of that? Okay, so I guess we'll start with today's material then. And what we're going to be looking at today is some advanced methods for sampling, in particular what are known as MCMC, or Markov chain Monte Carlo methods. The Markov chain Monte Carlo methods are a way of handling some kinds of sampling problems that would be hard to solve with the methods we've seen in the previous classes. And some particular examples of that are systems we've already seen, or that you've probably seen in other work that you've examined. So, for example, if you think back to the first class that we had covered, we had looked at a simple example involving protein folding. In that case, we were talking about a simulation of a fold of a protein on a lattice. That's kind of a discrete model of the shape of a protein. We might be interested in, let's say, sampling probability distributions over possible folds of that protein. So can anyone think of why that might be a hard thing to do? Well, it's in general going to be hard to sample probabilities of different folds of a protein, let's say different shapes on a lattice, because there's simply too many of them. If you've got more or less 3 possible positions for each link in a chain, you might have hundreds of links in the chain. Obviously, not every possibility or set of possibilities can really occur, but still you're looking at an astronomical number of possible ways the protein can fold. So generally, you're not going to have an easy time trying to figure out the probabilities among these, and you need some way of at least efficiently enumerating among the ones that are reasonably well represented in the overall probability distribution. So that would be an example of a hard distribution we might be interested in. Another one we might see would be involved in, let's say we're trying to model patterns of gene expression. We're trying to simulate gene expression within an organism. We may have many different genes, and their expression levels will influence one another. So some of these genes might be transcription factors, and those transcription factors might regulate expression of other genes, or they could be splicing factors, they could be involved in RNA degradation, lots of other things could be going on. And the result of this is that if we're trying to create a simulation that considers possible, let's say, levels of expression of gene 1, gene 2, gene 3, and so forth, we're going to end up with a set of variables that are highly correlated. There's going to be some complicated way that these different expression levels depend on one another, and it's not going to be easy to come up with a sample of a consistent set of expression levels and get an idea of whether we're sampling that correctly according to this complicated joint distribution applied by the model. Question?
Can you just give a specific example of what you mean by sampling?
And so sampling is basically what we had covered a couple of classes ago, where we would have, let's say, a probability density, maybe an exponential density with some parameter lambda, and we want to pick values according to that probability density. So we want to pick random numbers or random variables with some known distribution of those variables. That's what I mean by sampling.
But how does it apply to, let's just say, the protein folding example? What would one sample look like?
So a sample would be a fold of the protein in the protein folding case. But we wouldn't necessarily want to just see, let's say, the lowest energy fold. The protein is going to have some dynamics. It will probably shift, sometimes open up, sometimes there will be flexible pieces. So if we want to get what would be the equivalent of looking at that protein in its normal dynamics and just taking a snapshot of that at one random instant, that's what we mean by sampling. So that would be sampling one configuration of the protein. Does that answer your question? Okay, so that's the kind of problem we'll be looking at today. And what I wanted to do is look at a few basic methods for doing that. So a couple of standard methods for sampling from these kinds of hard probability densities, and then some basic tools we can use for accelerating those kinds of samples in cases where they don't work efficiently enough. And we've actually already very briefly seen one of the standard methods for doing this, one of the standard MCMC methods, and that's known as the Metropolis method. Right, so all of these MCMC methods will have the same basic flavor to them. What we're going to try to do is come up with a Markov model whose states represent the possible configurations of the, let's say, possible states of our protein or possible assignments of expression values to genes. The states are the values we're trying to sample among. And we set up the Markov model in particular so that the stationary probability, so the average probability over long runs of it, is the distribution we're trying to sample from. And then if we run the model long enough and just take a random state from a long run of the model, we will be guaranteed that we're sampling at least pretty close to the stationary distribution or pretty close to the distribution we're trying to sample. So that's the basic idea behind MCMC sampling. And we just want to see a couple of ways that that can work. Right, so are there any questions before I get to how the Metropolis method actually works? Okay, so the Metropolis method was originally proposed as something specifically for sampling from a kind of distribution you see in statistical physics called a Boltzmann distribution. And a Boltzmann distribution is the standard distribution you would have when you're looking at the thermodynamic equilibrium of something that has energies assigned to the state. So the protein folding example would be an instance of this. Any fold of the protein will have some free energy. So it might have free energy E1 in one condition, E2 in another, and so forth. And what a Boltzmann distribution says is that at the thermodynamic equilibrium, so on average over long enough periods of time, the probability of being in any one of these states is going to be proportional to e to the minus energy over Boltzmann's constant times the temperature, and then that's going to be divided by some universal scaling factor. So the fraction of time you spend in state 1 will be e to the minus e1 over kt, whole thing divided by c. Fraction of time you spend in state 2 will be e to the minus e2 over kt divided by z, and so forth. So that is a Boltzmann density or Boltzmann distribution. And the Metropolis method, as I say, was originally designed as a way of estimating Boltzmann distributions for complicated systems like the protein folding example. And in particular, giving a way of relatively quickly sampling among the reasonably well-represented states of a system that has a very large number of states. So we can illustrate how that works by taking a somewhat simpler example, and that would be a macromolecular complex. So I'm going to propose that we've got a system in which we've got a relatively small number of molecules. Let's call them A, B, C, and D. And these molecules come together to form some kind of complex, a structure that binds them all together. And I'm going to assume that this process proceeds through a reaction that maybe binds A to B, and then C and D are still kind of floating around free. And we'll assume that this is reversible and that there's some free energy E1 of this state and E2 of this state. We can then allow that maybe there are two possible things that would happen next. So maybe C binds to that AB complex, D is still floating around, or the D binds to the AB complex and C is still floating around. We can say that this has an energy E3, this has an energy E4, and those can also be reversible. And then in either case, we'll assume that this goes to a final state where all four of those molecules are bound together, and we have some energy E5. So that's going to be the setup of our system. I'm going to propose that what we want to do is create a Markov model where these configurations are going to be the states of the Markov model, and where the stationary distribution of the Markov model will be the Boltzmann distribution implied by these energies. Is that clear to everyone? Okay, so this is something that we would not usually really want to do in practice. So we would not want to use this method when we've got such a small system, because we can very easily analytically compute the Boltzmann distribution. So we know this has a probability e to the minus e1 over kt divided by z, this is e to the minus e2 over kt divided by z, and so forth. We can figure that weight factor out for each of these states. We can add up those weight factors to find out what z is, and then we can directly get the probabilities of each of these states. There's no point in doing this. I'm doing it as an illustrative example. So what the Metropolis method says is the following. The first thing we're going to do is define our states, which are the configurations we're trying to sample from, and I can just say that we'll call that state 1, so Q1, Q2, Q3, Q4, and Q5. And we're going to define a graph on those states. And in this case, we're kind of given a graph. So we could say that we've got Q1 goes to Q2, that goes to Q3 and Q4. Those go to Q5. It actually doesn't matter for correctness of the method that this is the graph. Even if this is the graph the reactions actually follow, we could come up with a completely different graph. So you could go Q1 links to Q3, to Q5, to Q4, to Q2. It can affect the runtime of the method. I'm about to tell you it doesn't affect the correctness. But for now, let's just assume this is the graph. It'll be a little simpler. And the Metropolis method then says that we're going to do the following steps. We're going to pick some arbitrary starting state. So let's say we're given some state Qi, which is the current state we're in the model. And we're going to pick a next state. So we're going to pick the next state as we go around the Markov chain as follows. Pick a random neighbor of Qi with probability 1 over d. And d here we will define to be the maximum node degree. So the maximum node degree is simply the maximum number of neighbors in the graph. So what would be the maximum node degree for this graph? 3. So Q2 has 3 neighbors, so that would be the maximum here. So we're going to pick that with probability d, and we're going to say that for stay in Qi with probability 1 minus di over d, where di will define to be the degree of node I. So if we're in state Q1 initially, then with probability 1/3, we pick state Q2. With probability 2/3, we just stay where we are in state Q1. Right, so we picked then our next state, and then we're going to do the following test. If the energy in our neighboring state, let's call that J, so let's call that neighbor Qj. If the energy in state J is less than the energy in state I, so we've picked a neighbor and that neighbor has lower energy, then our next state is Qj. If the energy of state J is greater than the energy of state I, then with probability e to the minus Ej minus Ei over kt. Next state is Qj, else next state is Qi. So let me just restate what this is saying. What we're saying here is you look at your initial state, you pick a neighbor with probability, in this case 1/3 of any possible neighbor. If we don't pick any neighbor, then we just stay where we are. Once we've picked the neighbor, we compare the energies in these states. If the energy has gone down, then we make the move, and then the neighbor we picked is the next state in the Markov chain. If the energy has gone up, then we use this probability, this e to the minus change in energy over kt. That gives a weight factor. If the energy has gone up, this thing will always be a number less than 1, so we can get a valid probability. Then that's the probability we take the move. Otherwise, we stay where we are. And that basically defines the Markov chain. You just keep doing that and over, and you're going to get a Markov chain that will move you among these states. So is that clear to everyone? Okay, so we can think of what the probabilities of the different moves would be according to this model, so we can come up with an exact assignment. To make the math a little easier, or at least less messy, I'm going to just declare that as we move from left to right here, the energy is going down. So the system is getting more stable as the complex gets built. And then we can say, in terms of this algorithm, what all of these possible probabilities would be. So if we are in state Q1, then we would consider our possible neighbors. We've only got one possible neighbor, that's Q2. We will pick state Q2 as our possible neighbor, or candidate next step, with probability 1/3. And then if we picked state Q2, then we're going to end up moving there. So the energy's gone down, so we're always going to take that transition. If we haven't picked state Q2, which would happen with probability 2/3, then we will stay in state Q1. So that gives us 2 of our transitions on this model. So is everyone with me so far? Okay, so let's say we've moved to state Q2. Can anyone tell me how we would pick our next state? What's the first thing we do? Well, the first thing we do is try to find a candidate state. With probability 1/3, it would be Q1. With 1/3, it would be Q3. With 1/3, it would be Q4. So let's say probability 1/3, we pick Q1 as our candidate state. And what's the probability we actually take that move to Q1? Well, it's this factor here, e to the minus change in energy. So it would be e to the minus E1 minus E2 over KT. So the ratio of the Boltzmann weights of those two states. So that would be the probability of taking the transition from Q2 to Q1. We could say a similar thing with respect to Q2 and Q3. We've got a 1/3 probability of picking Q3 as the candidate, since we've assumed the energy is going down here. If we pick that as the candidate, we always take it. And likewise, a 1/3 probability Q4 is the candidate. If we pick that, we always take it. And then there would be some probability of staying in state Q2. And what are the conditions under which we could stay in state Q2? Well, the only way it could happen is if we had picked Q1 as the candidate but decided not to take the move. So if we had picked that with probability 1/3, then with probability 1 minus e to the minus E1 minus E2 over KT, we would end up staying in state Q2. Right, so we could keep going through this, and we could keep assigning probabilities here and come up with the complete Markov model graph. And then we would end up with a model that we could simulate. And the assertion that we'll prove in a moment is that this will in fact create a correct sample of the Boltzmann probabilities. So if we run that long enough, the average number of steps that we spend in each state will be proportional to the Boltzmann weight of that state. The reason this is useful, though, on the graph. So if we were looking at, let's say, a more complicated example. So suppose instead of building a complex of 4 things, we were building a complex of 400 molecules. Then you would be talking about a very big possible graph, and you're not going to want to go through the exercise of even figuring out what the possible states are, much less computing the probabilities. What's useful about Metropolis is that you don't have to do that. So in particular, if you look carefully at the way the algorithm works, you should be able to notice that the only things you really need to know about are your current state and the immediate neighborhood of that state. So as long as you can look at your current state, you can figure out who the neighbors are of that state, and you can figure out the changes in energies to the immediate neighbors, you can run everything in this algorithm without having to ever explicitly compute the entire graph. And that's really what makes it useful, and the reason you would use it often for these situations where you're talking about very large graphs that are too large to represent in a computer. Right, so is the method clear to everyone? Okay, well, let's see then why this is a correct method. So why does it do what we claim it does? So one of the first things we're going to want to verify to see that this is correct is that we have a graph that is ergodic. The method isn't going to work unless it's possible to get from our starting state to every other state in the graph. To some degree, that's something we have to ensure by picking a connected graph, but we also will need to know, even if it's connected, that it's at least possible anytime we go from one state to another state to have some chance of getting back. If you go from Q1 to Q2 to Q3 to Q5, you have to know for certain that there's some path that will get you back to Q1 with non-zero probability for this to work. That, fortunately, is guaranteed pretty easily by the algorithm. So there's always going to be, for any 2 given states, some probability of going in each direction, as long as you don't have infinite energies. So as long as the energy isn't infinite, there will be one direction where your probability of moving is 1 over d, and the other direction it will be 1 over d times e to the minus something. So as long as that something is finite, then you're guaranteed you have the probability of going back. So we end up with an ergodic graph. So that at least guarantees that if you run this long enough, it's going to visit every state an infinite number of times, which is what we're going to need to get good samples. But we then need to prove some harder properties. And one of the first ones is that we're going to need to prove that the model has a unique stationary distribution pi. Can anyone tell me how we would prove that? So we saw a test, I guess last class, that you can use to prove that a Markov model has a unique stationary distribution. Does anyone remember what that is? We would want to show that there exists some n and some delta greater than 0, and this has to be strictly greater than 0, such that the probability of going from any state I to any state j in exactly n steps is at least delta. And that has to be true for all I and j. So that's the test we can use to prove that a Markov model has a unique stationary distribution. And does an arbitrary Metropolis model satisfy that? Yeah, so we can kind of come up with a hand-wavy proof that it does by basically just making one simple assumption. So if we assume that all of the energies aren't identical, then there has to be some pair of states that have different energies that are neighbors in the graph. And once you have that, you know that at least one of those states must have some self-transition probability. there has to be some probability you consider the higher energy state and don't take the move. And so we're guaranteed that somewhere in the graph there's going to be a node that has a non-zero self-transition. And from there we can basically come up with a way of building this by using the fact that there is, for any pair of neighboring states, there is going to be a non-zero probability of going in each direction. Basically what we can say is, if you take the diameter of the graph, which is the largest number of edges possible between any two different states, pretty much you can say that for n at least as large as twice the diameter, you can walk to this state that has the self-transitions. You can take a bunch of passes around that self-loop, walk to the other state you're trying to get to, and just make sure you take enough passes around this loop to get to whatever end you're trying to get to. And then you're guaranteed that each of these steps has probability greater than 0. So this is going to work for any n that's at least twice the size of the diameter of the graph. So it's not quite a formal proof, but it's at least an argument this is going to apply for any metropolis model graph, as long as you don't have infinite energies in it. So does that make sense to everyone? Okay, so that says that there is a unique stationary distribution, and we're going to want to show, in this case, that metropolis models satisfy an even stronger condition I've mentioned before, known as the detailed balance condition. And the detailed balance condition asserts that for any states I and j that are neighbors in the graph, the stationary probability of state I times pi ij, or the probability of transition from I to j, is going to be equal to pj times pji, stationary probability of being in state j times the probability of transition from state j to state I. And this will help us prove pretty easily that this is going to sample from the right stationary distribution that we're trying to create here. So does anyone remember how you would prove that a Markov model satisfies detailed balance? Well, I mentioned a test before, the Kolmogorov criterion. Does anyone remember what that is? The Kolmogorov criterion is the assertion that if we take the graph describing the Markov model, and we take any cycle in the graph, so any closed loop, you have some set of states, Q1, Q2, Q3, Q4, or whatever, then the product of probabilities of transitions taking that cycle in one direction is equal to the product of probabilities of transitions taking the cycle in the other direction. And if that's true for every cycle in the graph, then it satisfies the Kolmogorov criterion and it exhibits detailed balance. So we'll want to know that that is true of all possible metropolis model graphs. And we can show that by thinking about this in terms of the energies underlying these different states. In particular, we have energies that we are assuming are assigned to each of these states that we're visiting as we go around the cycle. And we would then have some change in energy from each successive pair of states. So we can call this, let's say, delta 1, delta 2, delta 3, delta 4, delta 5. And some of those transitions will have positive energies, and some of those will have negative energies. So the ones where the delta is negative, that means that we're making an energetically favorable change here. So let's say this one is negative. So what would be the probability of that transition if the change in energy is negative? So we saw that here, it's just 1 over d. So if you're taking a step that involves a negative change, then the probability is 1 over d. And if you're taking a step that involves a positive change, then the probability will be 1 over d times the e to the minus delta 2 over kt factor. So one way or another, we get some of these positive, some of them negative, and our final probability in product over the entire cycle is going to be 1 over d time to the power of however many steps we have in the cycle, let's say k, times these energy factors for the steps that happen to have an increase in energy. So we'll have the set of factors, let's say gamma of e to the minus delta I over kt, where these delta i's are the steps on which the energy is going up. And the product of a set of exponentials is just going to be an exponential whose exponent is the sum of the individual steps. So that's going to be 1 over d to the k, e to the sum of over all of these positive steps I of delta I over kt. So did everyone follow that? So then we just need to know one more thing about physical systems to tell us that actually going in one direction is going to give us the same product as going in the other direction. And can anyone figure out what that is? What's an important property of energies moving around a closed system back to your starting state?
A closed loop is 0.
Yeah, any closed loop, the energies have to add to 0 because energy is conserved. So when we get back to our starting state, we know we have to have had a net change of energy of 0. And what that tells us is that the absolute values of all of the terms that are negative going one way have to be equal to the absolute values of all of the terms that are going positive that way. And that means if you flip the direction, you get the same sum. You're just seeing the same energies from the opposite direction. So that's kind of complicated, not quite a formal proof again, but it's basically saying that this thing is going to be the same whether you go forward or backward. You're just getting the sum of all of the energies all in one direction, or taking the opposites, which add to the same thing in the other direction. So does that make sense to everyone? Okay, so that tells us that the metropolis model for any metropolis system exhibits detailed balance, and we can then use that to figure out what the unique stationary distribution has to be for any metropolis model. And I'm going to leave this here for a minute. All right, so if pi I pij equals pi j pji, then we can say that pi ij over pji must be equal to, or pij over pji must be equal to ij over ii. In this particular model, we know that if we are moving from some state I to state j, then let's just say for the sake of argument that we happen to be taking a transition where the move lowers the energy, or excuse me, the move increases the energy, so we're going to a less favorable state, then what's going to happen is that Pij is going to be equal to 1 over d times change in energy e to the minus Ej minus Ei over Kt. And Pji is just going to be 1 over d, because we're assuming that that's a favorable direction. So 1 over d's will cancel out, and we can separate out the two terms of the exponential to get e to the minus Ej over Kt divided by e to the minus Ei over Kt. And since we know that's equal to pi j over pi I, what this is telling us basically is that the ratio between pi j and pi I has to be proportional to their Boltzmann weights. And that pretty much is a proof that guarantees that if the ratio between the stationary probabilities is proportional to the Boltzmann weights, the only way to satisfy that is if all of the probabilities are the Boltzmann weights. It must be the case that pi I is its Boltzmann weight e to the minus Ei over Kt divided by some normalizing factor, and pi j is also its Boltzmann weight e to the minus Ej over Kt divided by the same normalizing factor. And if we just keep going through all of the states, what we've guaranteed is that the stationary probabilities from the model must be the Boltzmann weights. So that's why the metropolis method works. no matter how you design the graph, as long as you follow the steps of the metropolis algorithm and run it long enough, you'll get arbitrarily close to sampling Boltzmann weights. So does that make sense to everyone? Are there any questions?
There's a 1 over d to the k there. Is that the same as the Boltzmann?
Well, the 1 over d to the k is coming from the fact that every step has a 1 over d factor. So if you're going k steps around the cycle, then the product would have a 1 over d to the k
So
term.
the 2 k's are different, right?
Oh, yeah, I guess I should say this is kb, Boltzmann's constant. And this is just a number k. Any other questions? Okay, so that basically is why the metropolis method works. And we can then start to see some interesting properties of this that we would often want to know about if we're going to work with this in practice. One thing I'll point out, one kind of caveat about this, is that metropolis is often used as a simulation method for simulating discrete systems. And that's not actually a correct thing to do. It's commonly done, but it isn't necessarily correct. So metropolis, more specifically, is a thermodynamically correct model, which means that if you run it long enough, the fraction of time it spends in each state is going to be correct for the energies. But it is not a kinetically correct model. And what that means is that even though if you run it long enough, it will spend the right fraction of time in each state, the sequence of transitions through the states may be completely non-physical. It doesn't give any guarantees about that. So that's something to be aware of. You get the right stationary distribution if you run it long enough. You don't necessarily get the right sequence of states, so just be aware of that. And one other caveat, which we'll see a bit later how to do something about, is that the mixing time can be long. So does anyone remember what a mixing time is? So a mixing time is essentially the number of steps we need to run a Markov model before it gets close to its stationary distribution. It's a measure of how quickly it converges on the stationary distribution. And a metropolis model can potentially have an arbitrarily long mixing time. So that's something you usually need to be careful of. You don't know when you design a model like this necessarily whether it's enough to run it for 100 steps, or if you need 1,000 or 1,000,000 or 100 million. We'll see next week some ways to prove properties about mixing times, and hopefully later today some ways we can speed up mixing times if they're not good enough, but this is something you always have to be careful of. You have to make sure you're running your model long enough to get a good sample. If you run it for any finite amount of time, you could be pretty far from actually getting a good estimate of the stationary distribution. So does that make sense to everyone? All right, so there's one more important thing to be aware of with the metropolis method, and that is what I will refer to as a generalized metropolis. So basically, although metropolis was originally designed for Boltzmann distributions, the method actually works much more broadly than that. You don't need to have Boltzmann distributions to be able to create a Markov model that will sample correctly using the metropolis algorithm. In fact, the only thing you need to know is the ratio of stationary probabilities you're trying to design for any pair of states. So if you are given any kind of system, so any discrete system where you're trying to sample stationary probabilities, and you can set up an ergodic graph on it, so a graph that is connected among all the states, and you can figure out this ratio for any pair of connected states, that's actually all you need to put together a correct metropolis model. And we can kind of see why that is by looking at the algorithm here. So the first step here doesn't actually depend on the energies at all. We pick a neighbor with probability 1 over d, even if our model didn't have energies defined in it, we could do that. The second step depends on the energies. So we're asking, is the energy of the state we're considering lower than the energy of the state we started with? And we can actually figure that out without knowing the energies as long as we know this. So how would we figure that out? What test can you apply to this ratio pi j over pi I that would tell you whether state j has lower energy than state I? If this is greater than 1, then state j is lower energy. So if you are moving to lower energy, your Boltzmann weight goes up, you have higher stationary probability. So we can basically replace this step if Ej is less than Ei with the test if pi j over pi I is greater than 1. And then that step follows just as before. And we can also replace this thing here, this test, if Ej is greater than Ei, that's just asking if pi j over pi I is less than 1. We've got one more place where we refer to the energies here, and that's computing this factor, e to the minus Ej minus Ei over kt. Can anyone figure out how we could compute that given this ratio? Well, if we're given that pi j, I guess it's already written here, so if pi j is e to the minus Ej over kt divided by z, and pi I is e to the minus Ei over kt divided by z, then pi j over pi I is equal to e to the minus Ej minus Ei over kt, and then z's will cancel out. So in other words, this thing here is pi j over pi I. So basically, if we have an energetic system, so we're trying to figure out Boltzmann weights, we can just plug in this ratio in each of these places, and we now no longer need to refer to the energies. And what's maybe not so obvious, but is also true, is that everything about the proof still goes through. It doesn't matter that this ratio came from energies. No matter how we get these ratios, it all still works out. So that's the generalized metropolis algorithm. Basically, as long as you can figure this out for any pair of states, however you define the graph of the model, you get a correct sampler. So is that clear to everyone? All right, so let's see an example of that. So let's suppose we are trying to generate random strings of DNA. So we've got, a string of characters, A, C, T, G, G, A, C, C, and so forth. And we want to sample among distributions of these strings. We want to generate a random string of DNA. Then we can set up let's say, a Markov model to generate strings of DNA by just saying that each move of the model will correspond to picking one base and flipping that base. So that would define a neighbor relationship. We can say two sequences are neighbors if they differ in exactly one base, and then the set of neighbors of one sequence would be all of the bases times all of the ways of flipping the base. So if you have n bases, you'd have 3n neighbors. That is, our graph degree would be 3n. So that would be a potential Markov model we can put on sequences. And if you wanted to generate uniformly random sequences, we could just run that model exactly as I've described it with uniform probabilities, so equal probability on these edges, and that would work. But let's make it a little harder. And let's say we're trying to generate sequences that are rich in CG dinucleotides. So we want to generate sequences, and we're proposing that this comes from some region of the genome where you have an unusually large fraction of CG pairs. So that would be something that's not so obvious how we would do, but we could, as long as we have a model for this, come up with a metropolis sampler that will generate that. So let's say we decide that in this region of genome, we favor CG pairs by a factor of 2 over any other arbitrary pair of bases. So if we've got, let's say, a sequence AGG, and we transform that to ACG, then we would say that we've created a new CG pair, so that would have double the probability. Well, that's something where we would then have an easy way of coming up with pi j over pi I. We look at our two states. We can see that this state has some pi I. We don't necessarily know what it is, but this one has one more CG in it, so this would have a stationary probability of 2 pi I. That's going to be our assertion here. And that's pretty much all we need to know to design a metropolis sampler for sampling from this CG-rich sequence, or a CG-rich model of sequences. All we would need to do is come up with our graph, which we already have here. We would need to come up with our method for computing the change in ratios of probabilities between the states. And then our algorithm would pretty much follow. We would pick random base with prob 1 over n. So pick one random base to change. Pick a random replacement character with probability 1/3. So we've now picked among 3n possible neighboring states. Compute the change in the number of CGs. And then we can say pi j over pi I is equal to, let's say, 2 to the number of CGs. And then we just apply the metropolis criterion. So if pi j over pi I is greater than 1, then make the move. So we move to state, our new state j, else move with prob pi j over pi I, and then just go back to step 1 and keep doing this over and over a long enough number of steps. You'll get a sampler that is going to correctly sample your sequences according to this distribution that's favoring CG 10 nucleotides. So does that make sense to everyone? Okay, so that basically is the metropolis method, and that, as I say, is one of the major methods for simulating from these complicated distributions. Now there's one small thing that I put in the textbook that I'm not going to go through here, and that is the use of metropolis as a heuristic optimizer. Basically, there's a standard technique for optimization that is easy to use if you understand the metropolis method. This is known as simulated annealing. And the basic idea behind this is simply that if we can take any kind of discrete problem we're trying to optimize, turn its objective function into an energy, so literally just call the objective function an energy, so that better values of the objective function correspond to lower energy, then you can run a metropolis sampler and just crank down the temperature. So lower the temperature so it gets more and more favorable in terms of pushing towards lower energies. That gives you a heuristic known as simulated annealing, which tends to often do a pretty good job at optimizing for systems that are intractable or otherwise hard to develop optimizers for. So you can check in the book if you want to see an example of how you could use that to come up with a traveling salesman optimizer, but that is something I'm just mentioning as an aside. I'm not really going to go into it. All right, so any last questions about metropolis before I move on to our next technique? Okay. Okay, so the other major technique we would often use, the other major kind of MCMC sampler is something called a Gibbs sampler. And a Gibbs sampler is something we would typically use when we're trying to sample from a hard distribution consisting of a joint distribution of a large number of variables. So let's say we've got some function, let's call it probability x1 is equal to some value little x1, variable x2 is equal to some value little x2, etc. up through some xn, some current value little xn. We want to establish a probability distribution where we're assuming these are interdependent values. So the value of any one variable may have some complicated dependence on the current values of the others, and we want to sample from this distribution. So this is a situation where we would commonly use a Gibbs sampler. And the way we would do this is, again, to set up a kind of Markov model where the stationary distribution of the Markov model is going to be the joint distribution of the variables. So to do that with a Gibbs sampler, what we would first do is set up the state set of our model. And the state set is simply going to be the set of possible assignments of values to all of the variables. So in other words, if x1 is chosen from a set of values r1 and x2 is chosen from a set of values r2 and so forth, then the state set is going to be r1 cross r2 cross r3, etc. And the model, much like the Metropolis one, is going to be pretty simple. We can come up with a pretty simple set of rules that lets us take any assignment of the variables and then move to a new assignment of the variables, such that if we run it long enough, we'll sample correctly from the joint distribution. Now, unlike the Metropolis case, with a Gibbs sampler, we don't get to choose the graph. The graph is automatically implied by the method, and in particular, the Gibbs sampler is going to have transitions that take the following form. If we have some variables x1, x2, up through some xi, up through some xn, every transition is going to have the form of changing exactly one variable. So xi goes to some xi prime, and all of the others are held fixed. So the neighboring states of any particular assignment of variables are exactly the states where one variable and only one variable has been changed. And what the Gibbs sampler says is that that transition is going to have a particular probability. So the probability of going from this state where the ith variable has value xi to this one where it has value xi prime is going to be given by the following. 1 over n times the conditional probability the ith variable takes on value xi prime, given all of the other values are fixed. So x1 through xi minus 1 have the value that they have in both of these cases. Xi plus 1 up through xn have the value they have in both of these cases. And that's pretty much the entirety of Gibbs sampling, this basic rule here. The complications come because, of course, you have to be able to sample from that probability density. And the way the algorithm actually works is as follows. We pick our variable xi uniformly at random. So we pick any of the variables that we want to change. There are n variables. We have probability 1 over n of each one. We sample xi prime from the conditional density probability of xi given x1 through xi minus 1, xi plus 1 through xn. And basically that's it. Just like with the Metropolis model, we really don't need to know anything about the joint probability distribution. We don't need to explicitly create the entire graph of states. We just need to be able to do this. We need to be able to figure out for any one variable, if we freeze all the other variables, what is the correct distribution of values for that one variable. Right, so just like with the metropolis model, we can look into why this would be a correct way of sampling from our probability density. It should be obvious that this is going to give an ergodic graph, because any set of variable changes we make, we could always reverse those and just go back along the same edges. Our edges are always going to be bidirectional. So we're going to get an ergodic graph, and any sequence of changes we want to make, we could just flip one variable after another until we get to whatever other variable we're trying to get to. So basically you can get from any point A to any point B. This model will also exhibit detailed balance. And we can show that also pretty analogously to how we showed it with the metropolis model. So we can take some arbitrary cycle. We can consider what variables are changing in each of these states as we go around the cycle. Let's say we change variable xi on this state and hold all of the others fixed. And what we're going to get then is that this has some value, let's call it xi1 here, it's got some value xi2 here. Then the transition probability as we go in this direction is going to be 1 over n times the probability of moving to value xi2, conditional on fixing x1 through xi minus 1, xi plus 1 to xn. So that's going to be our probability of going in this direction. And we can simplify that a bit, or maybe not simplify, but transform it a bit by applying one of our basic axioms of probability, Bayes' theorem. And Bayes' theorem, for anyone who's not familiar with it, says that the probability of A given B is equal to probability of A and B over probability of B. And what that has to do with this case is that we can say that this is going to be equal to 1 over n times the probability of the assignment of all of the variables x1 up through xi minus 1, xi2, xi plus 1 through xn, divided by the probability of b, which is this thing here. So the probability of all of the variables except for that one assignment, xi up through xi minus 1, xi plus 1 through xn. And if we take the loop in the opposite direction, then we're going to get a similar factor from that edge. So in the opposite direction, we're going to get a factor of 1 over n probability of x1 through xi minus 1, xi1, xi plus 1 through xn, divided by probability of x1 through xi minus 1, xi plus 1 through xn. And this pretty much gives us what we need to get our proof here. So if we take the loop around this way, then we're going to visit one factor of this form when we go through this edge. And if we take it the other way, we're going to visit an identical factor when we go through that edge in the opposite direction. Whichever way we go, we're going to get a 1 over n term. So the only thing we have to worry about are these values in the numerators, which are simply the joint density of the entire state here. So if we call this Q1 and this Q2, we've got a factor of pi 2 here, pi 1 here. And that's basically all we need to complete the proof, because we're going to hit each of those at some point in our cycle, whichever way we go. We're going to hit this one moving through this edge when we're we're going to hit this one when we move through this edge when we're going clockwise, and we're going to hit that going through this edge if we're going counterclockwise. So basically, what this is saying is that every one of these factors is going to be hit the same number of times, whether we go clockwise or counterclockwise. So if you put all of that together, we get that a Gibbs sampler also exhibits detailed balance. Now I guess I skipped over the proof that the Gibbs sampler has a unique stationary distribution. Can anyone tell me why that would be the case? Well, if we have n variables, then to get from any one assignment of the variables to any other, we can just change each variable one and also have that satisfied. But basically what we're going to end up with then is that we have a model that exhibits detailed balance, has a unique stationary distribution, and that tells us that Pij over Pji is going to be equal to Pij over Pi. And we can then figure out what pi j and pi I would be by plugging in these values, pji and pij, which we've now already got written here. So if we take the ratio of these two terms here, then we will cancel out the denominators, we'll cancel out these 1 over n's, and what we're left with are the stationary probabilities that we want for state j and state I. So basically, just like with the metropolis case, if you just plug in the definition of Pij and Pji, you get back the right ratios, which proves that the desired stationary probabilities of the joint densities are the things that will come out of the model. So everyone follow that? Okay, so you don't necessarily need to know any of that to use these models effectively, but it's good to know that the Gibbs sampler, like the metropolis sampler, is a correct method. And we can then see an example of how you might use a Gibbs sampler. Right, so let's take an example from statistical physics known as an Ising model. So an Ising model is a simple kind of model where we might use a Gibbs sampler. And what an Ising model does is the following. We imagine we've got a set of states that are magnets. Well, I shouldn't refer to these as states. We've got a set of magnets, and we'll assume that a magnet has two possible positions. Either it's pointing up or it's pointing down. So an Ising model would be a way of saying that there is some energy of sticking two magnets together. And generally, if two magnets are pointing in opposite directions, they have a favorable energy, let's say minus g. You can get a minus g here. If they're pointing in the same direction, they would have an unfavorable energy, so let's say plus g. So we can say that this configuration of the Ising model has a total energy of minus 2g. And in an Ising model, you typically want to sample from the thermodynamic equilibrium of the system. Now, we could create a metropolis model to do this, but let's just try creating it as an Ising model. To do that, we would want to define our variables, and we can define one variable corresponding to each of our magnets. And we can say that the variable takes on two values. Let's say it's 0 if it, or let's make it +1 if it's up, -1 if it's down, and then this one would also have +1 or -1, and so forth. So that's defining now the range of possible values. The states of our model are going to consist of an assignment to each of the magnets. And that basically means it's going to be the state set +1 -1 cross +1 -1 cross +1 -1, and so forth. So we want to then define a Gibbs sampler that will give us a correct estimate of the distribution of assignments to these different magnets, and the way we would do that is as follows. Step 1 of the Gibbs sampler is take a random magnet. If we assume we've got n magnets, then we've got 1 over n probability of picking any particular magnet. And then what we would do is sample from the conditional density of that one magnet, assuming all of the others are frozen. So if we picked this magnet, let's say, we would compute what is the probability density, or what is the probability of it being pointing up, given that the one to the left of it's down and to the right of it's up? And what's the probability of it pointing down, given that the one to the left is down and to the right is up? We could compute that as follows. So we can say the probability xi is -1, given all of the other values, is going to be equal to e to the minus -1 times xi -1 plus -1 times xi plus 1 times g over kt. So that's going to be a Boltzmann weight. And if xi is negative, these will be positive terms. We get a favorable, or excuse me, the xi is negative, these will be unfavorable terms. So we get a negative factor here and an unfavorable Boltzmann weight. If they disagree, so if this is positive, we get a positive value for the exponent. So we get a good energy. And we're going to need to normalize that by the weight we would get for the -1 state. So exactly this thing in the numerator. Plus the factor we would get for the +1 state, xi -1 plus +1 times xi plus 1, g over kt. And this then would tell us the probability that one magnet would be in state -1. Everyone follow that? Okay, we could say the same thing for the probability it is in state +1. So that's going to be this e to the minus +1, xi -1 plus +1 times xi plus 1 g over kt, divided by the same numerator, or the same denominator we have here, e to the minus -1, xi -1 plus -1, xi plus 1, g over kt plus e to the minus +1, xi -1 plus +1, xi plus 1, g over kt. That tells us the probabilities of these two assignments. We pick one proportional to these two probability values, and we either flip this state or we don't, and then we just go back, pick another one, flip or don't. And then you run this a large number of steps. You see how often each magnet is in each position, and that we know will correctly sample from, in this case, a Boltzmann distribution if we run it for a long enough number of steps. So did everyone follow that? Have any questions at this point? Okay, so it's worth saying that both of these methods are actually usable not just on discrete densities. You can also come up with continuous or infinite state Markov models, in a sense, that will sample from continuous densities by these kinds of methods. So suppose, for example, we have some joint distribution on n variables that has a continuous point density f. So f of x1 to xn is the point relative probability of assignments at x1 through xn in a set of n variables. And we can define a set of conditional densities. So some fi is the conditional probability of xi given assignments x1 through xi minus 1, xi plus 1, up through xn. So let's say we can compute this for every value I. Then the same basic method works in the continuous cases and the discrete one. You pick a random variable, you sample from the now single variable continuous density of the value of xi, given all the other values are frozen, and you just repeat that over and over. That will give a correct sample from the joint density in the continuous case as well. We can see an example of that as follows. So let's say we've got some cavity and we're trying to see if how an ion might sit in this cavity. So let's say we've got a positively charged cavity, we've got some negatively charged ion, and this ion is maybe moving around in the space, and we want to know how often it's sitting close to this cavity position. We might propose that this has some probability density described in terms of two variables, f of xy, that's given as, let's say, some k, a scaling factor, e to the minus square root of x squared plus y squared. So in other words, you might say that this, the farther it gets away from the center of the cavity, the less favorable it is. This is just some proposed distribution it might follow. So let's say we want to create a sampler that samples from that distribution and gets a set of xy values that more or less give us some statistics on how often it's sitting close to that pocket. Well, we can come up with a Gibbs sampler just like we do in the discrete case. We would first have to figure out what our variables are. So what are our variables? X and y. So our first step would be pick x or y with probability 1/2 of either. So we can pick either one with probability 1/2. And let's say we pick x. Then what we would want to do is sample a new value for x from the conditional density of this thing given that we've got a fixed value of y. So let's say we are starting in a state x0, y0, and we're trying to pick a new x for that state. Then if we know the joint density of those two values, then we can get the conditional density. So that would be f sub I of x, given that y is fixed to value y0, and that's just going to be the following. It's going to be k square root, or k e to the minus square root x squared plus y0 squared. So this is going to be the value of the joint density with y fixed at y0. And then we just need to normalize that. And we would normalize this by the complete probability that y is y0. And we would get that by integrating over x. So integrating x from minus infinity to infinity of k e to the minus square root x squared plus y0 squared dx. That will get the correct normalizing factor here, and then we've got a density of one variable. How might we sample from this density? Yes, we could use the rejection method or the transformation methods, either of the methods we've seen before for sampling from a single variable density. And then we just do the same thing with respect to y. So if we happen to pick y, we would do the analogous thing. You get a density f of y with respect to, given that x is fixed at x0, that would be k e to the minus x0 squared plus y squared, normalized by the integral e to the minus x0 squared plus y squared dy. That would give a sampler that you could then use, or a density you could use to sample from y. So any questions about that? Okay, I'll also mention that Gibbs sampling, much like metropolis sampling, is commonly used or often used as a heuristic optimizer. So just like with a metropolis sampler, if you can come up with some system you're trying to optimize, where you have a set of variables, you can take the objective function of your optimization, treat that as some function of the probability of a given state. So a typical thing would be to say that if your objective is, let's call it c of x1 through xn, then you would say that maybe your probability is going to be proportional to e to the minus c of x1 through xn, come up with a Gibbs sampler based on that probability ratio, and then you get something that's likely to do a pretty good job of finding low energy, or that is high probability states that correspond to good values of your objective function. So any questions about any of that? Okay, so we've got a few minutes left here. I guess I'm going to briefly mention one final topic. I think we may need to finish this up next time, and that is what we can do if our models run too slowly. And there's a common technique for that known as importance sampling, which is basically a way of taking any kind of Markov model and adjusting it, usually so that you speed up its convergence. Sometimes that you speed it up, that is lower the mixing time for the entire model, sometimes that you lower it for a particular subset of states that are of interest to us. And the basic idea behind this is not too complicated. If we've got a model we're trying to simulate that has states Q1 to Qn, and it's got a stationary probability density values pi1 to pi_n, then the idea behind importance sampling is that we will create a biased sampler where generally we will try to skew it to favor states that we want it to get through to converge quickly. Often that will skew it to favor states with lower probability, or maybe you may want to skew it to favor states that are kind of a bottleneck in trying to get where you want it to go. So if you're looking at a physical system that has to pass through some energy bottleneck, you might favor those states. But the basic idea is simply assign a set of weights, W1, W2, up through Wn, such that you change the probabilities of those states. So we would then say that we have some biased sampling probability, some biased density, pi, which is going to be equal, or pi hat, where each element of pi hat will be pi I times Wi, normalized by some z factor, which we compute by basically summing up all of the pi i's and Wi's. And any of the kind of sampling methods we've used, it ends up being relatively easy to come up with a way of imposing whatever weights we want. So let's say we're looking at the protein folding example I mentioned before, and suppose we know that it takes a while for a protein to collapse. You start with an unfolded protein, and you want to get it to the folded state, but you know it has to do a lot of trial and error to get there. We might bias that model to get to that state we care about more quickly by throwing in a weight function such that we're giving extra energetic favorability to collapsed states. You can often measure that using something called the radius of gyration of your protein model, let's say, where we can say that for any given state, so any given fold of the protein, it has some radius of gyration I, which is basically kind of the maximum extent of that protein fold. And what we can do is throw in a weight function, Wi, which we will say is, let's say, e to the minus Ri. So when we have a big Ri, an unfolded protein, you're putting a very unfavorable weight on it. A compact one, you're putting a favorable weight on it. Well, if we're doing, let's say, a metropolis sampler, then all we need to recognize to put these weights into the model is that anywhere we had a term pi j over pi I, so anywhere we were considering two adjacent states in the model, we just replace that with pi j e to the minus rj over pi I e to the minus ri. You plug that into your metropolis model, and you've now got a metropolis model for your biased sampler. So it's going to be skewing the weights according to this thing that's biasing it to fold more quickly. And then all you need to do is take out that skew at the end. So you count from this distribution, which is now going to be sampling that biased weight pi hat, and you just replace your biased weights by taking out these energies. So if you sample that there's some pi I for a state I, then after you're done sampling, you throw in an e to the plus ri, and then you just normalize by the sum of all of these over all of the states you visited, and then what you get back is a sample of your original density pi, but a sample that is biased to get more quickly to an accurate sample of the states you care about. So that's basically the big idea behind importance sampling. Does that make sense to everyone? And so if you work in statistical physics or structure modeling, you'll often see the term umbrella sampling. Umbrella sampling is basically the same thing. It's often called umbrella sampling because if you have some structure where you have some measure, what's called a reaction coordinate of the energy of this or the progress of a reaction, then an umbrella sampler is basically an importance sampler where you throw an umbrella-shaped weight over a region of the probability space that you care about so that you're biasing it to get into here quickly. So you can think of this where maybe we had the opposite sort of system. Let's say we had a protein that was folded and we were interested in what happens when it unfolds. Probably it doesn't do that very often, but we can throw an umbrella around it that biases it towards unfolded states. And then, even though it may very rarely unfold in practice, you get a sampler that unfolds it very often, but through this kind of correction, you can get an accurate sample of how often it's in that unfolded state and what it looks like, what it's doing when it's in that state. So does that make sense to everyone? Okay, well, I think we're out of time, so maybe we're not meeting on Thursday. Please bring your homework to my lab, and you're all welcome to attend the talks that get, but not